Hello everyone, here is my progress report for this semester. My name is Zhang Sujia. My topic is enhancement of decomposition method for Crampton circuits. My program is CAEE 950. My student ID is 2022210434. My supervisor is TX Dr. Zari Ismail Rizman. As we know, the rapid expansion of computational demands in the digital age, coupled with the constraints imposed by Boolean logic, has propelled researchers toward exploring alternative computing paradigms. Classical computing architectures are nearing their limits, compelling science to seek novel solutions to address imminent computational bottlenecks. Quantum computing, grounded in the principle of quantum mechanics, presents a revolutionary pathway. The advent of quantum algorithms such as Thor integral prime factorization and grover data search has demonstrated that the potential that utilizing quantum bits enable computing speeds and efficiency that far surpass those of classical systems, and quantum computing, as the novel paradigm rooted in quantum mechanics, demonstrates exceptional computational power and holds significant potential in fields such as machine learning, quantum chemistry, and information security. Although aforementioned quantum computing prototype has demonstrated certain advantage in solving classical interactable problems, they still suffer from several physical limitations. These limitations primarily include a limited number of qubits, extremely short qubit coherence time, and restricted qubit connectivity, high gate operation error rate, and the absence of error correction capabilities. The Crampton logic circuit mapping, which is the progress investigate, is one of the key issues, as aimed to adapt Crampton circuits to physical devices while presenting functionality by introducing auxiliary Crampton gates or equivalent gate replacement. Quantum circuit mapping fundamentally involves the decomposition and transformation of quantum circuit due to the physical constraints imposed by NISQ device. It has a significant impact on the number of quantum gates and the success rate of quantum computations. The restricted connectivity between quantum bits is an objective physical constraint in current superconducting NISQ architectures. To satisfy this constraint, auxiliary quantum gates are often inserted. However, excessive use of auxiliary gates greatly increases the probability of errors in the quantum circuit. The progress focuses on the technique for circuit composition and optimization in quantum circuits, aiming to reduce the number of quantum gates, improve the efficiency of quantum decomposition, and enhance computational accuracy. The research holds the great significance in enhancement of the foundation software of NISQ computing devices and advancing the practical implementation of quantum computing. Here is the problem statement. The restricted connectivity between quantum bits is an objective physical constraint in current superconducting NISQ architectures. Excessive use of auxiliary gates greatly increases the probability of errors in the quantum circuit, and the insertion of auxiliary quantum gates will increase the cost of quantum circuit implementation and reduce the execution efficiency. Here is the literature review part. As we know, quantum algorithms can be represented by quantum circuits, and quantum computers, like the classical counterparts, undergo a computation process to convert high-level programs into low-level programs that are closely related to the physical implementations. This enables their execution on quantum processors. The accompanying figures illustrate the transformation process and the corresponding quantum gate library for quantum algorithms on NISQ devices. There has constraint hindered the direct execution of specified functional quantum circuit on quantum computing devices, necessitating mapping procedures like compilation in classical computers to satisfy the physical constraints of the devices. Quantum logic synthesis constructs a netlist composed of various types of quantum logic gates, leveraging the behavioral level description of the circuits. A universal gate library for quantum computation can be constructed using only single qubit gates and 2-qubit gates. And after that, research attentions have shifted toward quantum gates decomposition using extremely low-level gates libraries. She introduced qubit global ordering and local ordering strategies, aiming to minimize the number of sweep gates. This strategy played a crucial role in defining the key steps of quantum circuit mapping and have significantly influenced subsequent research. Chevy decomposed quantum circuits into sub-circuits and utilized the minimum linear arrangement algorithms to determine global ordering of qubits for each sub-circuit. This approach resulted in an average reduction of 28% in the number of sweep gates compared to the baseline algorithms. ENCORE explored a look-ahead search strategy for the next n subsequent quantum gates during qubit local ordering, leading to an average reduction of 27% in sweep gates. The research on circuit mapping has entered a development phase where real NISQ devices are the target platforms. Following the introduction of superconducting NISQ architectures by companies like IBM and Google, the qubit connectivity topology is not limited to regular one-dimensional or two-dimensional lattice structures, but can adopt arbitrary structures. They present a shift mapping algorithms known as SABRE, which achieve global optimization of the initial location of qubits through backward traversal technique. Moreover, their device a weight cost function with look-ahead capability. Compared to the mapping method in reference, this approach not only achieved an average reduction of 10% in sweep gates, but also significantly reduced the execution time. Sheach approached the two primary sub-problems in quantum circuit mapping, namely qubit allocation and gate neighborhood scheduling, as subgraph in morphing and token sweep problems. They employed corresponding algorithms for problem solving. Compared to the SABRE algorithm, this approach averages averages a reduction of 16% in auxiliary quantum gate count. So here is the research gap. At present, research has shown some effectiveness in optimization, yet there remains ample room for improvements in areas such as time complexity and mapping cost. And the existing methods for quantum circuit mapping have limitations in terms of qubit allocation strategy and gate neighborhood scattering. There is still considerable room for optimization in reduce the number of quantum gates. And here is my research question. First, enhancement of quantum circuit decomposition algorithm. My research focused on the developing advanced algorithms that improve the efficiency of quantum circuit decomposition, aiming to reduce the overall execution time and minimize the occurrence of errors. Second, quantum circuit decomposition and gate count optimization under the constraints of restricted connectivity. And this research will investigate techniques for decomposition quantum circuits while considering the restricted connectivity between qubits. The objective is to optimize the mapping of quantum gates onto physical qubits, resulting in a reduction of the number of quantum gates required for the circuit implementation. And the research objective is 1. Development of efficient quantum circuit decomposition algorithms. The primary objective of this research is to design and develop novel algorithms that decompose large-scale quantum circuits into smaller and more manageable subcircuits. The goal is to improve the efficiency of the decomposition process, reduce error rates, and maintain the accuracy of the original circuit. 2. Investigation of optimization strategy for quantum circuit mapping. This objective involves exploring different strategies and techniques to optimize the mapping of quantum gates onto physical qubits. The search aims to decompose quantum circuits while satisfying the physical constraints, resulting in reduced circuit depths and the number of required quantum gates to enhance the overall performance of the circuit. 3. Evaluation of the performance of the proposed optimization algorithms. This objective involves conducting comprehensive performance evaluations and comparative studies of the developed decomposition and optimization algorithms. Measurements will be taken for factors such as time complexity, circuit error rates, circuit depths, and quantum gates count to ensure the effectiveness of the proposed method. The efficiency, scalability, and practicality of this method will be analyzed by comparing them with traditional decomposition method. And the research method is 1. Problem definition. Clearly define the problem of quantum circuit enhancement. And 2. Literature review. Conduct a comprehensive review of the existing literature on quantum circuit enhancement algorithms. Identify and analyze various approaches, techniques, and algorithms proposed by researchers in the field. 3. Problem modeling. Develop a formal material model to represent quantum circuit and their optimization objects. 4. Algorithm design. Propose a novel quantum circuit enhancement algorithm based on the insight gained from literature review and proper modeling. 5. Pre-processing. Implement pre-processing technique to analyze and manipulate the input Crampton circuit before the optimization phase. 6. Optimization technique. Select and apply appropriate optimization technique tailored the specified objective and constraints of the Crampton circuit problem. 7. Performance evaluation. Design a confidence set of experiments to evaluate the performance of the proposed Crampton circuit algorithm. And 8. Analyze and discussion. Analyze and interpret the experimental results obtained from the performance evaluation. Discuss the strengths, weakness, and the limitation of the proposed algorithms. And 9. Conclusion. The scope of study is 1. Focus on Crampton circuit decomposition technique. 2. Analyze resource optimization. 3. Crampton gate optimization under the limit connectivity constraints. 4. Performance evaluation and comparative analysis. And here is the Gantt chart of my PhD. Because I just started with my PhD journal, so I haven't published any paper yet. So the status of publication and the others is 0. And now I'm going to write the thesis and planning to finish DRP in the next semester. Thank you.